Good morning, class, and welcome to this lesson on Electrostatics 6, electrical potential versus electric potential energy. These are not the same thing. These are not the same thing, and we'll discuss what they are, despite the fact that they are almost the same in name. Today, we will be able to describe how electric potential and electric potential energy are related. So that's all this lesson is going to be. It's a very difficult concept to understand, and so let's give it a shot here. Okay, so the best way I think to describe how this works is to relate it to something we know, namely gravity and potential energy. In this picture right here, we have a picture of a ball moving from point A to point B. Okay, so it has a larger height at A and a smaller height at B. So at this point right here at A, it has a gravitational potential energy. And this gravitational potential energy is defined as mgh. Okay? And we'll call it mgh of A. It also has a potential energy at height B, and this gravitational potential energy is defined as mghb. So it is changing height from A to B. Okay, and as it goes down, it is losing potential energy because the height is now smaller. And so what we normally would say is that the work done due to gravity excuse me for a second. The work done due to gravity is equal to the change in potential energy, or also known as the gravitational potential energy of B, which is final, minus the gravitational potential energy of A. So gravity does work on the ball. It applies a force, the force of gravity, over a certain distance, and that is what our change in potential energy is. So if this ball had 100 joules of energy here and 20 joules of energy here, there was 80 joules of work done because it fell at 80 joules essentially. So that is gravitational potential energy. It's a concept that most students can get. Well, electric potential energy, I'm going to call it as EPE, is kind of the same thing. Let's assume we have a positive test charge, our positive test charge, and there are two parallel plates. We have a positive plate and a negative plate. And we know from our discussion on electric fields that there is going to be an electric field between these two plates, and it's going to be a uniform electric field. It's going to be a uniform electric field. So if we place this test charge inside this electric field, the closer we get to the positive end, the more energy it has. So just like in our discussion on height, the higher a ball is off the ground, the more energy it has. The closer we get to this end, the positive plate end, the more electric potential energy it has. So we'll call this electric potential energy at A, and then it's going to have less the closer it gets to the negative side. It's kind of like a ball falling. Kind of. It is similar, it's not the same. Because these plates can be oriented in any direction. It could be positive like this, any direction. So the work done is equal to the electric potential energy of B minus the electric potential energy of A. And as you can see here, B is going to be less than A. B is less than A because it's falling, and so our work is going to be negative. Our work is going to be negative. So if we have a charge moving in an electric field, it is gaining or losing energy. Okay, if just like we have a ball changing height, it is gaining or losing energy. So that's all nice. Now, I don't think I need this anymore. No, I'll leave it there. Let's look at this. Let's look at this diagram here. With electricity, we're more concerned about energy per charge. How much energy is there per charge? Because we're not looking, like in this example, we're looking at a single mass, right? We're looking at a single mass. But with electricity, it's really hard to envision or use a single charge. to use a single charge. So we're looking at a per charge basis. So we have this equation, work equals the electric potential energy of B minus the electric potential energy of A. And so we're going to divide everything by Q0 because we want to know how much energy there is per charge. And so this concept, work divided by charge equals energy divided by charge, is what we call voltage, V, voltage. And voltage, or volts, is known as electric potential, electric potential. And the unit is volts or joules per coulomb. As you can see here, we have energy, which is in the unit of joules, divided by charge, which is the unit of coulomb. So we have this electric potential voltage versus electric potential energy. So electric potential energy is really the work done in an electric field. It is measured in joules. Electric potential, not energy, is voltage. So it is the energy per charge. It is the energy per charge. So in this field, we have, this has a voltage here, the energy per charge here. This has a voltage here. So our equation has just become VB minus VA is equal to electric potential energy of B minus the electric potential energy of A divided by Q0, our test charge, which is the same thing as our negative work from A to B divided by Q. So notice we have the same equation. Our work equals our difference in energies. Okay? But if we divide by charge, this now equals the difference in the voltages. And so our delta V here can equal the change in electric potential energy over Q0, or our delta V can equal the negative work done from A to B over Q0. So these are our equations. Okay? So let's look, oh, excuse me. So here we have a graph showing a higher potential to a lower potential. And so let me add this picture here. So if we look at this example, this is a lower potential area, this is a higher potential area. If we have a positive test charge, if we have a positive charge, so we're looking at a positive charge closer to A positive charge will accelerate from higher electric potential to lower electric potential. So for example, here we have positive and negative. It will accelerate downward because this positive is going to push it down and it's going to accelerate down. Okay. However, a negative charge will accelerate from lower electric potential to higher electric potential, which is where this analogy of comparing it to gravity kind of breaks down, because like if this was our example of gravity, things always fall down, right? They never fall up. They always fall down, but based on the charge, they might accelerate down or up. And so we have to take that in consideration. So that's where the analogy kind of breaks down. So we have this concept of electric potential and electric potential energy. So to kind of show you or finish this off with our equations here, we have two equations here. We have our equation for energy. So this is our energy, our electric energy is equal to Q0 times V. We are used to this concept of energy. Energy should be something, as a physics student, that you have been fully exposed to. Kinetic energy, potential energy, rotational energy, elastic energy. These are all things that we've been going over, and they're kind of easy to, they're easier to comprehend than this. And then we have this concept of force. Force equals Q times E. So these are two things we're used to working with. However, with electricity, it's easier to work with voltage, which is energy divided by charge, which you can see is we just divided by charge here. And then the electric field is force divided by charge, because with charge it isn't a single object. It is a multitude of electrons, and so it's easier to break it down in a per charge basis. So just like our electric field is force per charge, our voltage or our electric potential is energy per charge. So what I'd like to do now is finish this off with a concept of the electron volt. An electron volt. Some of you may have heard this term before. So what is an electron volt? An electron volt um, is how much the potential energy, how much the potential energy changes when one electron moves through a potential difference of 1 volt. Okay, how much it moves through a potential difference of 1 volt. And so basically we have electric potential energy is equal over Q is equal to voltage. So so how much energy is one electron going to get through 1 volt? And the charge on one electron is negative 1.60 times 10 to the negative 19 coulomb. Okay, and this is just magnitude. And so what that means is the sign doesn't matter. And so basically, 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. It takes that much energy to move an electron through a potential difference of 1 volt. And so we're going to be seeing this term a lot more. So an electron volt really is a unit of energy. It really is a unit of energy. It is not a voltage. It is not a voltage, despite the fact that it has volt in this term right there. And so I'm going to move on from this video and start and explain a little bit more about electric potentials. And I'm also going to start doing some problems later on. And so if you want to see this more in action, keep watching.